to start by thanking the organizers for putting together this night school and giving me the opportunity to speak here, as well as to the rest of you for staying until the end of the day. So this talk will be about entanglement in quantum magnetism, and I've sort of split it into two subtitles here that reflect kind of the traditional condensed matter theory perspective on entanglement, which is based on states and wave functions, which are things we can't access in experiment. So there will also be a second part that addresses observable quantities that are called witnesses that also give you information about entanglement. So the outline of this talk is essentially to start by reminding you about some properties of quantum mechanics and some results in there. And then I will proceed basically into this kind of states and witnesses characterization. So we're primarily interested in looking at entanglement, of course, in systems like quantum magnets and quantum materials more generally. And although this is to some extent kind of a marketing term, what I mean by it is solid state and condensed matter systems where your basic degrees of freedom, they really do interact quantum mechanically, and you need to keep track of this in order to see what happens even at large scales. So that means that we do have some of these properties of quantum mechanics actually show up in the materials themselves, even though we might have on the order of 10 to the 23 atoms in there. So the first kind of key property to remember is that of quantum superpositions of states. So instead of this kind of classical idea where we have a system in some definite states, and in the case of a two-level system, we can just think of them as 0 and 1, right? In general, actually, we have these mixed states where we have a superposition that's characterized by some coefficients between the states. And this is sort of one of the key ideas that lends power to new applications like quantum computing, because you can really use this superposition to compactly represent a lot of classical information. The second key idea I want to talk about briefly is entanglement. And I think entanglement really is best introduced by defining what it isn't. So if we think about some system in a pure state, like a ground state, represented by these black dots here, there are some kind of entangling correlations between them. So if I go ahead and I basically cut the system into two pieces, this is called a bipartition, into region A and region B. If I then can write this pure state of the system as just a product of a state that lives in A and a product that lives in B, then I have a so-called separable state, meaning it's not entangled. Conversely, if I can't come up with a way of actually writing it as a product like this, then I have a non-separable state or an entangled state. And probably the simplest example that you will have seen of this is just a spin 1/2 singlet that shows up in hydrogen molecules and the helium atom and so on, where we have two sides. So we can write, for example, this normalized state as up, down, minus, down, up. And then, of course, if you try to separate it like this, you will not succeed. And it has some other a remarkable consequence of this is, of course, that if you measure the spin on this side, and it turns out to be in an up state, then the other one will be in a down state, even if they're really far away. And this is the type of physics that has been demonstrated very clearly in kind of few body systems, and was actually rewarded with the Nobel Prize in physics just 2 years ago to Aspe, Clauser, and Zeilinger. So in their approach, what they actually, in the most famous experiments, what they did was just to consider what happens if you have a source of two correlated photons, and then you compare their polarizations later on. That turns out to give you a way of determining that the system has to be non-classical in nature. And more specifically, this is all based an initial idea from John Stuart Bell in the 60s, that you can come up with correlation functions and combinations of them, so-called Bell's inequalities that can only be met by quantum states. So in particular, there is this example of the so-called CH-SH inequality, where here A and B represent the two photons, and 0 and 1 the two polarization states. So you can come up with this kind of funny-looking linear combination of expectation values, and it turns out that if that combination exceeds the value of 2, then you know that the state of these two photons cannot be classical. It has to be either an entangled state or something more complicated that they're estimating. And then there is also some kind of upper bound even in a quantum system that's a result of Searle's. Now, as a condensed matter theorist, of course, it's natural to wonder if this same kind of physics survives also in many-body systems. And in general, if we have some kind of generic system, there will be correlations between different sites, and in general, some of them will be weak enough that we can explain them with classical physics, but some will tend to exceed these corresponding classical bounds and have to be of quantum origin. And this is what I will call quantum correlations. Now, this isn't something that happens only sometimes. It turns out that if you go ahead and define a measure of quantum correlations called quantum discord, that's a quantum information concept, you can actually show that almost all states in generic Hilbert spaces will have some degree of non-classical correlations like this. Yeah?
Can you explain the difference between correlation and entanglement?
I think that is sort of the theme of the talk, yes. So the point, I guess, is that unless you know the state, you cannot try to do this kind of approach where you try to come up with ways of decomposing it into separable pieces. But what you can often do experimentally is to measure correlations, and then if they satisfy certain inequalities, you can infer that there is entanglement there. That is the idea of the talk. Yeah, okay. So we have this idea that this is often present in generic quantum many-body systems. So it leads to some natural questions like, does this actually matter in materials? Can we quantify entanglement and quantum correlations in materials? And can we maybe even use them? And this using them question is perhaps most relevant in the light of some recent quantum information sciences applications. So in general, this field views entanglement and other types of quantum correlations as kind of a resource to be used. So in superconducting quantum computers, for example, they think of entanglement as a kind of a resource to do operations with. And similarly, in quantum communication, there's a lot of talk about how different parties will share entanglement over a distance. And even in quantum sensors, that's an idea that's perhaps more closely related to condensed matter. There, the idea is that basically you prepare a sensor in some kind of quantum state, and that allows you to get higher metrological sensitivity or some other desired property. Now, through a lot of theoretical works, it's been built up the idea that also quantum many-body systems, whether they are atomic systems or condensed matter systems, often from a theory side of view, we look at a lot of entanglement in model systems and so on. And they actually, these kind of quantities show up in various interesting phenomena that I will discuss later. But there is this large question, essentially, that if an experimentalist grows some sample of a crystal like this, how do you actually tell that it can be used in some kind of new applications like this? Do we have an entangled state that we can develop into some new system, or do we not? And not everyone wants to do what Mike did and spend 10 years before getting an idea about the answer. So it would be very nice to have a kind of a quicker probe to rapidly test this. Okay, so I will now go to the state and wave function point of view. So the most common measure you will see in condensed matter theory papers and so on is the entanglement entropy. So the idea is that we take some generic Hilbert space and we just split it into two, bipartition. This is called bipartite entanglement, which has nothing to do with bipartite lattices. It's just that we split it into two. So this can be done in real space, like I've sketched here, or momentum space, or whatever you want. And then you look for the reduced density matrix of one part of the system. So that's done by tracing out the degrees of freedom in the other part. And then, for example, we can define the von Neumann entanglement entropy or other entropies. But the von Neumann one is just given by this kind of trace of the reduced density matrix times the log of the reduced density matrix, which of course if you diagonalize it and use the eigenvalues of rho A, it has this nice diagonal form. So this formula looks very similar to things like the Gibbs entropy in statistical mechanics, except that it rarely vanishes at zero temperature. Rather there, at zero temperature is often where we have the most important effects of entanglement. It also, at least in this form, it looks very similar to the kind of Shannon entropy that shows up in classical information theory. And we can actually think of it in similar terms. Now the problem is that this whole construction relied on us knowing the initial state described by this density matrix rho, which usually you don't in an experimentally relevant situation. Although it has actually been done in some small-scale cold atom systems where you can do quantum state tomography, and in some specially engineered systems with photonic chips and so on. And even though it's not immediately relevant to experiments on condensed matter, it's worth looking at it a bit more closely because it tells us a lot about the structure of quantum antibody states. So if we draw some kind of random-looking network and we single out some region A of it here in this kind of light blue, and then if you look carefully, you will see that these sites that are in purple, those are kind of the edge states that have some kind of connection to the sites outside of the blue area. So there are sort of two main possibilities. So the one that one might expect in general is when you have a state psi where the entanglement entropy is kind of extensive and it grows with the size of the system, of this subsystem A. So that's what's known as a volume law. And that's something one should expect in general for kind of typical states. Many excited states and Hilbert spaces are of this form. But there is also a second important class of states, the so-called area law states, where this the entanglement entropy instead grows only as the size, not of the subsystem, but the size of the boundary of the system. So that's the area law here. So in this case, the entanglement really is holographic. So this is exactly what happens in these famous calculations on black holes, for example. But it also occurs in a large amount of ground states in condensed matter systems, and especially for systems with gapped ground states. And that particular result is what actually allows things, numerical techniques such as the density matrix normalization group, matrix product states on tensor networks to work, because it reduces the complexity of the state we need to represent a lot compared to the generic cases. And this is also one reason why DMRG in finite temperature is so much harder than for ground state calculations, for example. And even though it does this, it turns out that if you go to higher dimensions, it's not always so easy to reduce the complexity of those states anyway. So there's this paper by G and Isert where they show that even if we can reduce the generic picture of volume law states down to some small area of area law states, when you go to higher and higher dimensions, there is only really a small number of them that can be efficiently represented with tensor network states, which is part of why those methods struggle to go beyond 1D quite often. Okay, so this is kind of a view of the theoretical types of entanglement. And now I want to mention some places where they actually show up in condensed matter. So I already mentioned the matrix product states and tensor network methods. Perhaps the most important area where they show up is in a lot of like novel states of matter, like topologically ordered states, quantum spin liquids, and so on. So these states, they're often really defined in terms of their entanglement entropy and how that scales when you put it on in spaces with different topology. So I don't know how to measure that particular entanglement, but other cases like quantum critical systems described by conformal field theories, thermalization in quantum systems, and so on. These are effects that really follow. These are effects where the theoretical investigations of them often take the entanglement entropy as one possible lens to look at it. And then there is this whole idea of topological quantum computing, where you use a topologically ordered state that has some kind of anionic excitation that we can maybe braid around there. So this is stuff that often isn't mentioned much in textbooks so far, but I think these two books are quite nice resources for these kind of views and giving a quantum information view on a lot of states in condensed matter. But with that said, if we have covered the states and we've covered where these kind of entropies show up, a big question really becomes if we can directly detect entanglement in experiment on condensed matter systems. So some of the past activity in this direction has really been to utilize kind of very special ground states or that have special signatures, or where you can do very close comparisons with theory. So for example, if you can observe fractionalized quasi-particles, then you know usually that you have some entangled state. But there are also other cases. So this paper from Czeslaw Bruckner et al., they looked at spin systems that dimerize. So everywhere you have basically two spins pairing up and forming singlets. And then when you look at the interdimer spin-spin correlation function, if that exceeds classical bounds, then you can infer that you have entanglement. So of course, S dot S, you know that can go up to S times S plus 1. But in classical physics, it can never exceed S squared, right? So for spin 1/2 systems, the classical line really is this 1/4 line, and everything at lower temperatures here indicates some kind of entanglement. And then in other approaches, people have done really more sophisticated arguments, I guess. So in this paper on a square lattice antiferromagnet, their argument is basically that the vanishing spectral weight in this region here is a signature of resonating valence bond physics. And you really have to look into the details to trust them. Yeah?
As you said, the S squared is limited by S times S plus 1. So it's 3/4 here, if it's a spin half.
Right. That's
it reaches 1 when temperature goes to 0.
Yeah. So I think the value here is 0.9, which is within some error bars that were there in the original experimental paper. But then this theory paper sort of removed them. But they point out that, like, I think the error bars are like, it's 0.9 plus minus 0.2 there. So it's consistent with 0.75, I agree.
Okay.
Anyway, the point I want to make here really is that you can make these kind of convincing demonstrations of entanglement in condensed matter. But in this past approach, it's been very model dependent. So if you change your system slightly, this will no longer work. So a more general approach is to use what's known as entanglement witnesses. So this is a method from quantum information where you come up basically with observables that that if they satisfy some inequality, you can infer that your system is in a certain class of entangled states. So you can think of them as this kind of like order parameters for certain classes of entangled states. So much like the magnetization in a ferromagnet detects ferromagnetism, but doesn't detect antiferromagnetism, you can imagine having an entanglement witness that when it's large enough detects one class of entangled states but not another. So if we sketch a Hilbert space like this, in general there would be some region of separable states, and a large number of states with some entanglement. And then if we have some observable O, when it's large enough, it can tell us that we are in this sliver of the Hilbert space, for example. So the strategy I will describe here is really to use witnesses that can be defined in terms of measurable correlation functions. And in part because I started this project while I was at Oak Ridge, the idea will be correlation functions that we can measure in terms of neutron scattering. And this is an experimental technique that really measures spin-spin correlation functions. And it does that very cleanly. And it does allow for getting the data in absolute units, which is very important when it comes to these entanglement witnesses. And then another reason, of course, is that especially spin-1/2 systems, they're two-level systems just like qubits, so it makes a lot of sense to start there rather than electronic systems. So the basic idea of the method is that you have neutrons coming in and scattering off a sample of some material, then you collect them, and then you trust your neutron scattering colleagues that they treat the data well enough that they obtain what's known as the dynamical spin structure factor. So this is really just a Fourier transform of this kind of local spin-spin correlation function at two different positions and two different times. And from there, we can reconstruct a lot of the information of the system. So I want to go through a couple of these entanglement witnesses that we have used so far. So the first and the simplest is this one tangle. So basically, in this case, I take the system and I split it into A and B, where now this region A contains a single site. And if I do this for a pure state of a spin-1/2 system, I can construct a reduced density matrix quite straightforwardly. And it has this simple form where it's just a 2x2 identity matrix plus some weighted polar matrices. And from this, I can define an entanglement witness known as the one tangle, which just becomes 1 minus 4 times the magnetization component squared at this single site that we've identified here. So this is something that if you have a translation invariance, you can estimate this just from Bragg peaks. And in general, it will basically vanish if you have a fully classical factorized state, but it can be as large as 1 in a fully quantum disordered state. And it quantifies sort of entanglement between the single site and the rest of the system. So the second one is to consider two sites. And I'll let them be, in general, I'll let them be separated by a distance r like this. And then again, for spin-1/2 systems, we can determine the reduced density matrix. And even at finite temperature here, there turns out to be a valid entanglement measure called the concurrence. That in general, it's quite a complicated function of two-site equal time spin-spin correlations. So I'm not even writing it out. But it can be determined for any kind of symmetry of the state that you might have. So what this will do is it will really quantify the entanglement, the pairwise entanglement between these two sites and the rest of the system. But then you can also define a two-tangle, which is just the sum of the squares of the concurrences. So that quantifies the total pairwise entanglement in the system. So this is a quantity that's been around for a while, but it has some drawbacks for a lot of the systems we're actually interested in. So in general, it turns out that two-level systems like spin-1/2, they have a finite amount of entanglement that they're willing to spread around, which is a concept known as quantum monogamy. So if we are in a system where the two sides are kind of tightly bound like this, and you have strong correlations between those two sides, then concurrence is really good at detecting this. So in dimerized systems, it's strong. But for a lot of quantum spin liquids and so on, where actually we have superpositions of singlets connecting any number of sites, each of these connections weakens the concurrence and makes it impossible, basically, to witness entanglement with this particular tool. So we expect it to be small in general in quantum spin liquids, and you can actually show that it vanishes exactly in the Kitaev spin liquid. So that brings us to the third witness that Simiao brought up in his talk today, which is the quantum Fisher information, which is really kind of a tool from quantum metrology, where they've constructed this interesting functional f of q that depends on the density matrix rho and, in general, some operator A. So we can write down this sum over a complete set of states k and l, some matrix element, and then we weight it by these eigenvalues of the density matrix. So if it looks like it comes from nowhere, well, it has a kind of direct physical interpretation in metrology. So the basic idea is that we imagine having this operator A acting on a system, and then we want to ask what kind of response does that induce. So if it couples and it produces a phase theta, then the original density matrix will change through this kind of unitary evolution, and then we can ask, how precisely can I determine this phase theta? So the variance of theta, delta theta squared, turns out to be bounded from below by this quantum Kramer-Rao bound, where m here is the number of independent measurements, and f of q is this quantum Fisher information. Yes? Theta is some phase that couples to a generic operator A. So this is a central result of metrology. But where it became quite interesting was the development in 2012, where two different groups showed that the quantum Fisher information, in turn, is bounded by the amount of entanglement in the system. So they found this relation, and I will ignore this term here today. And n here is the system size. But the really interesting variable here is this k, which is known as the entanglement depth. So I showed you before bipartite entanglement, but you can generalize that to, say, tripartite or quadpartite entanglement as well, with more and more partitions like this that you study. And it turns out that entanglement depth tells you that if you have an entanglement depth of k, the minimum number of partitions you need to actually decompose your state in such areas will be k plus 1. So k equals 2 here, for example, will imply that we have at least 3 particles entangled at minimum in the state. And as you see, this is an inequality here. And the consequence of these two inequalities now is that quantum entanglement is necessary to get higher and higher precision in measurements. And the next interesting development that came in 2016 from this paper by Hauke et al. Was that they showed that we can actually, at thermal equilibrium, we can actually relate this directly to a linear response experiment. So now, as long as this operator A is a local bounded Hermitian operator, we can define this QFI density now, where I just divide by the system size. And it turns out to just be an entity integral over some tanh function here that plays the role of a filter. times dynamical susceptibility that we can measure with spectroscopy. And what this filter function does is it essentially suppresses the lowest energy scattering, where we can have incoherent classical fluctuations and so on, and it keeps the higher energy, the finite energy scattering, essentially, that's larger than KBT. So what this now allows us to do is to kind of flip this previous logic around and say that if we do a measurement and we get that to be precise enough, then we can actually infer that the system has to have some degree of entanglement that's quantified by this entanglement depth K. So, and then if I put, oh yeah, I should continue with adapting this to neutrons. So in inelastic neutrons, we take this formula again, and then this imaginary part of the dynamical susceptibility can be related to this dynamical spin structure factor I showed you before. And there are some prefactors in what the spin operators are weighted by, but if you go through the math and look at unpolarized neutron scattering, for example, then we can define a new quantity that I call the normalized QFI. That's just the QFI density divided by 12 times the spin length squared. So whenever this exceeds the value of an integer m, I know that the system must be at least m plus 1 particles entangled. And if we measure this with neutrons, then really this is Fourier transform of a local response. So this will pick up some kind of local entanglement. So unfortunately, this doesn't really find the topological entanglement that we hope to find, but there is more work in progress on that. So by now, I showed you this figure before, but by now we have several witnesses. And then if we can have multiple witnesses indicating entanglement of different types, we can really start thinking about doing kind of triangulations of where we are in Hilbert space and so on. And of course, I showed you these 3 different types of entanglement so far. So with that, I would like to turn to some experimental examples of this where it's been applied. Let me remove that unnecessary plot right there. That's in the way. Okay, and we're back. So this system, potassium copper fluorine 3, it's been known for a long time that it's a really excellent realization of a spin 1/2 antiphonetic Heisenberg chain that has S.S interactions along the chains with the exchange of 34 MeV and then much weaker interchain couplings that induce some kind of magnetic order at low temperatures. And I need to click back into the window. So we have both experimental neutron scattering data and finite temperature DMRG simulations of the spin structure factor. And then if one goes ahead and extracts the QFI from here, we get this kind of red experimental curve and the blue DMRG curve. So what this shows is that we can actually, at high temperatures, we can't really tell if a state is entangled or not. But below 150 Kelvin or so, these bounds, these inequalities indicate that the system has at least bipartite entanglement. And then there's a region with at least tripartite, and then at least quadpartite entanglement at the lowest temperatures. One can compare that to theoretical expectations for higher spin chains, indicating that in general, it's harder and harder to witness entanglement when the spin length grows, indicating some kind of quantum to classical crossover like this. And we can also go ahead and do the other witnesses real quick. So the one tangle below the ordering temperature is reduced from 1 because of the order, but it's still quite substantial. And then if we look at spin-spin correlations, you see that they're only really exceeding this classical bound of quarter for nearest neighbor. So quickly, these kind of concurrences die out even in spin chains. And actually, the 2-tangle, initially we found that the experimental result disagreed a lot with the DMRG result. But this is a consequence of essentially the subtraction of a phonon background. So if we mimic the same in the DMRG data and mask the low energy scattering, we get much better agreement. So the second example will be a different system. That's cesium-2 cobalt chlorine 4. So this is a spin 1/2 transverse field XXE chain, now with much smaller energy scales, 0.23 MeV instead of 10 times as much. So we have SXSX, SYSY, and SCSC along the chain, but now there is an easy plane anisotropy of 0.25 here. So this is a system that has a really interesting phase diagram, actually. It's quite rich. So at 0 field, and then at some finite critical field, the system is described by conformal field theory, where from theory we know that the entanglement entropy should basically grow as log of the size of the embedded system, the size of like this region A in the system. But there is also a factoring field here close to the second critical field where the ground state is exactly classical, and you can write it down exactly. And again, we have inelastic neutron scattering, this time as a function of field rather than temperature, and corresponding DMRG calculation. So there is some disagreement here at high fields, where it splits due to some interchain coupling I'm not including in the DMRG calculation. But certainly the qualitative agreement is quite good, especially at lower fields. And one can go through and look at the entanglement that's again being controlled by the field here. So in the entanglement entropy, we see this kind of critical scaling, the two critical fields. If you look at the 1-tangle, it really decays. Both the 1 and 2-tangle really decay to 0 at the factoring field, and then they come up again. And here there is some disagreement between the 1-tangle between experiment and the DMRG, which we think is due to some hidden order in this material, actually, that wasn't studied in the Bragg peaks that was used for the this calculation. And then the QFI is somewhat trickier to deal with in this case because of having a field and anisotropies. You end up having a lot of polarization factor effects that suppress the entanglement you can actually witness. So if we just do it directly on the experimental data, the most we can ever see is this teal line here and indicating bipartite entanglement. But if you go ahead and try to use DMRG, for example, or maybe polarized neutron scattering to undo these polarized factor effects, we can kind of correct the neutron scattering data and see at least tripartite entanglement. The second thing to notice here, though, is that as we tune the magnetic field to the second critical point around 2.15 Tesla, if I remember correctly, we kind of see that the QFI doesn't really witness a lot of entanglement here. So what's going on is that at this second critical point, essentially all of the spectral weight is exhausted by the emergent polarized order. So what this shows you, again, is that we really need more than one witness. So it turns out that as a mathematical problem, there is never going to be a single witness that will actually address all kinds of entanglement. And in experiment, we're even more limited, right? Because it has to be something we can observe as well. But at least this kind of QFI based on spins works at kind of low fields where you don't have too much of a polarized phase. And then finally, I want to flag another result where my collaborator, Alan Shai et al., what they looked at was this new system, new triangular system, potassium erbium diselenide, that's believed to be a J1, J2 triangular antiferromagnet that's close to a quantum spin liquid phase. And since it's close to this kind of quantum critical point separating an ordered phase and a quantum spin liquid phase, what they find is that entanglement witnesses really pick up signals from this quantum critical point. So if you work at this momentum decay point, the QFI is actually 4-part entangled even in this system. So, how much time do I have? Okay, I'll spend some time now to tell you a little about the spatial structure, because so far I've just given you some numbers of how much entanglement there might be in the system, and this will give a little bit more insight about how it's actually distributed, I think. So if we recall this form of the expression I had for the QFI, then the two things to note is that it depends on this susceptibility that I've written in momentum space and this quantum filter function. So it turns out that there are a number of quantum filter functions that will actually do the trick. And the one that identifies the quantum Fisher information is only one of them. There are other quantities known as quantum variance and Wigner-Jonas skew information and so on. And if we generalize this to a function h of x, we can just plug in appropriate forms of h of x and get out various kind of quantum information ideas there. The second thing is that if we Fourier transform from momentum space into real space, what this gives us is actually a general form of spatial quantum correlations. Because again, they still have this filtering function where they filter out the incoherent classical part and leaves the quantum part. And if we have measured S of k and omega with enough momentum coverage, we can do this Fourier transform also on experimental data. And we did that again on this potassium copper fluorine 3 system. So what happens then if you compare sort of what I call the total correlations, which is S.S, is that in the ordered phase, they become kind of long-ranged, but then above TNL, they decay with distance like this. But then the quantum correlation functions, on the other hand, they decay with the finite decay length at all temperatures, which is due to how this filter function leaves out the kind of the classical ordering there. So this, I think, is the first time this kind of length scale of quantum correlations has been measured experimentally, and it was, which has been argued to exist through theory before. And if you go ahead and actually get the estimates of the length scale from these decaying correlation functions, in yellow here is the length scale we should expect from the total correlations, and you see we have the data points here, and then the solid line from quantum Monte Carlo simulations on 100 times 10 times 10 spin chains. So in the simulation, it really diverges at the Niel point, the Niel temperature, whereas this quantum correlation length scale remains finite, and it actually remains comparable in length to the entanglement depth that I mentioned earlier. So another thing we uncovered through these simulations is actually that one can see very clearly how the quantum monogamy appears. So if you look at uncoupled chains, they will not order magnetically, and generally the total correlations will decay like this, and the quantum correlations will reach out further some distance like this. But when we start coupling the chains in 3 dimensions, enabling magnetic order to occur, the quantum correlations along the chains actually become shorter ranged, because now I'm beginning, as a spin 1/2, I'm beginning to share some correlations with neighbors along these directions as well. And this is something that if you have enough, in this experiment, we only really had the momentum coverage in 1 dimension, but in principle, you could do an experiment where you have it, the full 4-dimensional scattering data, and can get information about the dimensionality system quite directly like this. So I want to spend some time to give you an idea about some of the future directions in this field. And I think one important direction is to go beyond neutron scattering, because from the theory point of view, it really isn't limited to neutron scattering. A lot of this is either quantum information or like linear response-based ideas. It would be very interesting to look at strongly correlated systems. In this case, Kuiper ladder, but I'm sure we can come up with many other systems of interest. So one thing I think will be very interesting is in the future, if you have this experimental data on entanglement and quantum correlations, then you can start using that to constrain theoretical modeling on systems we don't really understand, as well as some of these spin chains that I showed, especially when you go to 2D systems and so on. There's also a lot of room, I think, to design more witnesses or come up with different kinds of combinations of them to optimize finding different interesting states of interest. There's been this idea of actually using data-driven approaches to identifying optimal witnesses. And in principle, a lot of these ideas could also be applied to out-of-equilibrium contexts, where you might be able to address things like light-driven materials and capture entanglement dynamics experimentally. So beyond neutron scattering, some of the things that have been done quite recently is that Stephen Blundell managed to apply to some muon spin relaxation data on a triangular lattice antiferromagnet. There's also been proposals on using time-resolved resonant inelastic X-ray scattering to actually measure the time-dependent entanglement in strongly correlated electron systems from Matteo Mitrano's group, among others. Some other possibilities that I think are interesting is to instead look at things like non-resonant inelastic X-ray scattering and so-called EELS, electron energy loss spectroscopy, especially if you have a momentum-resolved version of this. So what this probe is the dynamical charge structure factor instead of the dynamical spin structure factor. So this lets you do things like actually look at entanglement between density of electrons in systems, rather than this kind of spin sector entanglement I've been discussing today. And I think there's a lot of room for more directions here. And I know there have even been some suggestions on ways of doing this with single particle Lagrange functions and so on. On the strongly correlated electron side, I think there are a lot of really open questions about the structures of how these quantum correlations behave. In general, the quantum information people have developed a lot of tools that we have been able to use for spin 1/2 systems, but they're not directly usable for kind of electronic systems. There's one really large question is how do we actually deal with entanglement between the spin and charge sectors? If there's some experiment where we can access both at the same time, like RIGS, that might be useful perhaps. There's also a lot of subtleties, it's mathematical subtleties about how you deal with indistinguishable fermions if you try to look at particle-particle entanglement instead of lattice-site entanglement. Another idea that I think is quite powerful is that this QFI and other types of quantum coherence measures, it's really been proposed that they can serve as kind of magnifying glasses for the quantum critical fluctuations above quantum critical points. So this is something that would be really quite interesting to look at some enigmatic critical points like in strange metals. This material or some recent proposal as Simiao mentioned earlier. And the conclusion, I think, is essentially that quantum information, whether you access it from kind of the wave function side or the witness side, it really gives new ways of thinking about many-body states in real materials. And in particular, spectroscopic experiments are very powerful ways at extracting quantitative information about non-classical correlations in these systems. And one thing I want to highlight there is that I didn't describe any kind of new experiment. I just described new ways of analyzing data. So this really is making use of information that was hidden in data all along. And I've also been describing a way of doing this with model-independent witnesses. So that may be limiting in some cases, like the optimal witness might be something that really makes use of your knowledge of the system. But on the other hand, it makes things very flexible, and you can apply them even to very poorly understood systems. So with that, I'd just like to thank my collaborators, especially the two main experimental conspirators, Alan Tennant and Alan Chai, as well as a large number of other people that have been involved in these papers, and also you.
Any questions?
I'm curious how you normalize the data, let's say from transcategory or exponential.
Mm-hmm.
Do you use some sort of sum rule?
Yeah, so I think that tends to be the best way of doing it, actually, to normalize by some rules when it comes to neutron scattering data. There are also other ways where they have like specific kind of transitions and things. There is some kind of vanadium standard that they can use in neutron scattering. But then the modeling of the whole experiment and like your sample holder and everything becomes a bit more involved, I think. But in principle, you can do it purely from experimental inputs like that as well. But for spin systems, it's also quite easy to do it. But it's much easier to just do it with the sum rule, I would say. But yeah, when you get into like trickier multi-orbital electron systems, I suspect you will have to use these other methods.
I was wondering whether you've thought about how to probe a single fermion, single electron state.
So I've been avoiding that a bit, but I know Robert Koenig has this approach where he basically comes up with the fictitious doubling of a system and then argues that you can define a Hermitian susceptibility within that space. And I think that paper is still under review, but hopefully that could be a way forward, right, to actually be able to probe entanglement. But, well, he was thinking mostly about STM, I think, but I think ARPUS would be very interesting to be able to use.
Is it possible to factor in the experiment?
Well, as I said, it's been done in cold atom and photonic systems. So what you can do is either basically do full quantum state tomography. You can't do that in condensed matter, of course, because that the complexity of that grows, the number of measurements you need to do grows exponentially with the system size, I think. The other approach that has been done is really if you have engineered systems where you have well-defined modes, then you can do kind of a replica trick where you have one system that you want to measure and one that basically copies that. But I don't see that being easily applicable in materials either. So that is a big part of what inspired work into these kind of witnesses instead.
Yes, so for the quantum Fisher information format,
Yeah.
whether it's only uniquely applied to the spin susceptibility or to any correlator.
So I think there are a couple of things to say there. So in this approach, it's completely general. So you can apply it to any operator A. And I think for it to hold here as a normal bound on entanglement, you want these A's to be local, bounded, and Hermitian. And for this step to work, where you relate it to linear response, you also want thermal equilibrium. But like this proposal that does it with time-resolved Ricks, for example, they've shown one way of essentially relaxing this thermal equilibrium condition. So there may be ways around that for a lot of experimental techniques, essentially. But you still need some ways of normalizing your data to use it. And yeah, so, as Miao asked, I think there is this approach by Robert Koenig that might also relax the need for these operators to really be Hermitian. So, but still, I think you want them to be local and bounded at least.
There's another question.
Mm-hmm. Yeah, I think you're right. If you want to use this quantum Kramer-Rao directly, this M describing the number of independent measurements, it really, either you prepared copies of your system, I guess, or you've let it basically go back to its initial state. And I think that kind of assumption corresponds to the thermal equilibrium assumption down here as well. So in the general picture, it really depends on what operator you want to measure, right? In this case, it has to be something that can be measured for linear response measurements. So in the neutron scattering, the unpolarized neutron scattering, in general, you have some linear combination of the spin operators that are perpendicular to the momentum you're measuring.
Yeah. So because I find it interesting that when you look at the spatial structure of this entanglement, right? So usually we sort of have the two spin correlator in the real space theoretically, but in your measurement, somehow that in your connection you have also quantum filter information, right? So how you define quantum information in the filter? That's due to the experiments.
Sorry, what again?
The edge, right? You have in your real space.
Yep.
You know, the structure, you also have the quantum filter.
Yes.
Right? So whether that's a form of the quantum filter is really specific, or you have the, that's maybe I just used.
So I think the main properties of it is that it should go to 1 as the temperature, well, as this x. The entire argument goes to infinity. And I think it should be linear in x at low x. Yeah. And then it turns out that this linearity at like low h bar omega over kbt, it seems that we can actually relax that quite a bit. So we actually tried even the most kind of stupid filter function, if you will. So just doing a step function. And that actually seemed to have the same kind of scaling properties of the distance decay as whether you use a tanh function or a Langevin function, as is plotted right here. But yeah, I think you want it still to suppress the low energy scattering, and then precisely how you do that doesn't seem to matter all that much, actually.
Yeah, because in your DMRZ calculation,
Mm-hmm.
the chi itself, right, in principle, should also have the temperature in general. whether you're DMRG, whether you get to the, because that's a T equals L. So then you have the temperature effect and go to the edge. But in principle, I can calculate the car approach and low temperature.
Yeah, with DMRD, we can do it for finite temperature. So here, in this case, we're actually showing some quantum Monte Carlo data, because it turns out that the interchain coupling actually shows up in this formulation. But that's also finite temperature.
All right, let's thank the speaker again.